Back in 1924, physicist Louis de Broglie, that's his name spelled up there, made a very bold hypothesis. He said, let's imagine that all matter is actually probability waves. And to be more specific, he said all matter have a wavelength given by Planck's constant divided by the momentum of whatever it is. A reminder, Planck's constant is 6.626 by 10 to the minus 34 joules seconds. A very small number, which is why quantum mechanics only generally applies on very small scales. So let's work it out. Let's imagine I'm walking down the street, so I'll have a mass of about 70 kilos, and I'm going at a velocity of about 1 meter per second. So my momentum, remember momentum, which is normally written as P, is, if you're not close to the speed of light, just mass times velocity, which is about 70 kilograms meters per second. So what's my wavelength? Am I really a wave? Well, yes, according to de Broglie, I have a wavelength which is 6.6 by 10 to the minus 34 all over 70. So 6.6 is roughly 7, so we'll cancel that with a 7, giving us 10 on the bottom, so that's about 10 to the minus 35 meters. Okay, so that is why I don't diffract through doors and round corners. Well, to be precise, I do, but the diffraction, if you remember, depends on lambda over d. So if I've got a 1 meter wide door, a lambda of 10 to the minus 35, that gives a very, very small diffraction angle. So this is why quantum mechanics is not a big problem in my day-to-day life. But now let's consider something very much smaller. Little electron, little baby electron, moving at 1 meter per second, which is actually pretty slow for an electron. Now in this case, the momentum is going to be the mass of an electron. Now the mass of an electron is rather small, about 9 by 10 to the minus 31 kilograms times the speed of 1 gives a momentum of about 10 to the minus 30 kilograms meters per second. So its wavelength is going to be 6 by 10 to the minus 34 over 10 to the minus 30, which is going to be about 7 by 10 to the minus 4, which is just a bit less than a millimeter. Quite visible length. So if you do have subatomic particles moving at slow speeds, which is actually a very big topic of research here at ANU, slowing down things like atom lasers to very slow speeds, you can start getting quantum mechanics on scales that you can actually see with the human eye. But most of the time, the quantum mechanical scales are far too small to actually see with the human eye. However, as we will see, while you can't normally see quantum mechanics with the human eye, it can still have very big effects on the nature of matter.